Assalamu alaikum. Welcome to the third lecture. Let's continue refrigeration cycle. In previous class up till now we have studied what are the types of the refrigeration cycle. So basically we saw that there are two main types, gas or air cycle, and then the vapor cycle. In vapor cycle we further classified as a vapor compression and vapor absorption cycle, and then we continue with the vapor compression cycle, and we saw the fundamental working principle, different component, how the refrigeration system based on the vapor compression cycle is working. Now vapor compression cycle, they can be studied either based on the reverse Carnot cycle or ideal vapor compression cycle. So let's first discuss reverse Carnot cycle. In case of we also called it as a Carnot refrigeration cycle or a reverse Carnot cycle because it is the reverse of the Carnot cycle. As we saw in the case of the heat engine, it works opposite to that. That's why it's called a reverse Carnot cycle. Now in case of Carnot cycle, you can see the four component like the evaporator, compressor, condenser, and then the expansion device. Expansion device can be like throttling device, it can be turbine. So let's see how it is working. Now as I discussed previously, in case of evaporator absorb heat in the cooling space. In cooling space we place different items, milk, food, vegetable, anything. So the heat from that item is absorbed by that liquid refrigerant. So as a result of the phase change, we have vapors here. Those vapors are compressed by the compressor to a high pressure, high temperature. So the heat absorbed from the evaporator and as a result of the compression is rejected to the ambient air. And then we have the high pressure liquid here. So high pressure liquid is further expanded, and then we got the low pressure and low temperature vapor. So this process keep on continue. Now let's see the theoretical baseline. So let's see this TS diagram of the reverse Carnot cycle. So let's say what is happening in the process, let's say 4 to 1. 4 to 1 is basically the refrigeration effect. So this is the refrigeration effect that we want to produce. This is our desired effect. The amount of the heat that is removed from that refrigeration space. So that amount of the heat that is removed from the refrigeration space is basically, as we discussed in the theory, that's basically equal to that heat, basically QL, that should be equal to the mass flow rate of the refrigerant times delta H, pH, where pH is the enthalpy difference of the phase change, right? So that QL, which is also called the refrigeration effect. So that refrigeration effect is a constant temperature phase change process. So if we draw on the TS diagram from 4 to 1, right, from 4 to 1, this is a constant temperature, right? 4 to 1, that's just a constant temperature. This is just a phase change process. So this is called the enthalpy of the phase change, delta pH. And then the second process is compressor process. So how can we model compressor process? Isentropic compression. So that means the process from 1 to 2 is a isentropic compression. So that means S1 is equal to S2. And then next is the heat rejection process to the atmosphere. So again, this is again a constant temperature process from 2 to 3. This is a constant temperature process, right? So the heat rejection is again constant temperature process from 2 to 3. And then the last one is the in which we convert the high pressure liquid into low pressure liquid, low pressure and low temperature liquid. So we use an expansion device. Again, how can we model that expansion device? Let's say turbine, that we could model as isentropic expansion. So this was 1 to 2 was isentropic compression. So this is isentropic expansion. So this is how the refrigeration process is modeled based on the reverse Carnot cycle, right? So these are the four processes. So Carnot cycle consists of reversible processes which make its efficiency higher than that could be achieved in actual cycle, right? Then why discuss the Carnot cycle if it is unattainable idea? Because we discuss in case of the heat engine that due to a certain limit it is not applicable. Even then we discuss this. There are two reasons for that question. One of the reason is it serves as a standard of comparison. I mean, this is like a benchmark. I mean, every cycle, whether that's a gas turbine, IC engine, we compare the performance of that actual cycle with some benchmark, and the benchmark is Carnot cycle. And the second reason is it provides a convenient guide to the temperatures that should be maintained to achieve maximum effectiveness, right? And now let's discuss the COP of the Carnot cycle. Now, unlike the heat engine, in heat engine we use the thermal efficiency, but here we are going to use coefficient of performance in the refrigeration system. It is because the output in the process 2 to 3 is usually wasted. That's why instead of using thermal efficiency, we are going to use the COP or coefficient of performance. Now you can see how can we define the net work output here. You can see out of these processes, one is the heat absorption, another one is heat rejection. So the difference of the heat absorption minus heat rejection, that will give you the work input. We can say net work, right? So the net work is basically the heat absorbed in the evaporator minus heat rejected in the condenser. So this is 4 to 1 is the heat absorbed and 2 to 3 is the heat rejected. That value will be negative because you can see the area, that value is smaller, that value is larger. So net work is negative. I mean, net work input is negative. Why it is negative? Because this is a work input to the compressor. In case of work output, normally it is positive. I mean, we consider the sign convention. So that means process 2 to 3, the heat transfer during the isothermal process, we have two isothermal. Heat absorbed in evaporator is also isothermal process, whereas heat rejected in the condenser is also isentropic process. So let's say this is the heat absorbed in the evaporator, let's say heat rejected in the condenser, that's isothermal process. Similarly, heat absorbed in the evaporator, it is also isothermal process. We know from the theory that's TH, I mean this is the TH, this is TL. So TH S3 minus S2, similarly Q4 to 1 is TL S1 minus S4. Whereas this is an isentropic expansion, this is isentropic compression. So that means S1 is equal to S2, similarly S3 is equal to S4. So we may write S2 minus S3 equal to S1 minus S4 because S1 is equal to S2, similarly S3 is equal to S4. Now the net work output is equal to heat rejected minus heat absorbed. I mean, just to take the positive value. So if we put those value, I mean these above value, so we'll get this value. And then the COP of the Carnot cycle is the heat absorbed divided by net work. So Q1 to 4 is the heat absorbed, I mean refrigeration effect, divided by W net. So if we put those values, since this value is equal to this value, so this will be cancelled out. So the COP of the Carnot cycle is TL divided by TH minus TL. So that COP, I mean of the Carnot cycle depends on the two temperature only. One is the low operating temperature and TH is the high temperature. This is basically the ambient temperature, right? This is the condenser temperature, mean the ambient temperature. So that means COP of the Carnot cycle depends on two temperature. One is the temperature that we set inside the condenser, that low temperature, and this is the ambient temperature, outside temperature. So how can we increase the COP of the Carnot cycle? Either to maximize this. If we maximize this, then the COP will be maximized, right? By maximizing TL, target temperature, set temperature in the evaporator. If is higher, then the COP of the Carnot cycle is higher. Or the other way is minimizing TH. I mean the ambient temperature is lower, then again the performance of the COP of the Carnot cycle will be higher. That's why in summer season the performance of the refrigerator decreases. Why? Because in summer, I mean the ambient temperature is increases. So if it is a higher, then COP will be lower. Whereas if we compare the COP of the refrigerator with the COP of the air conditioner, I mean in case of refrigerator, the set value, the set temperature TL is lower compared to the air conditioner. In air conditioner, the set temperature is normally 20 to 25 degrees C, whereas in refrigerator the set temperature is 5 to 8 or 10 degrees C. So that's why the COP of the air conditioner is higher than the COP of the refrigerator. And then what are the limitations that we cannot adopt Carnot cycle for the refrigeration cycle? One of the reason is the difficulty of achieving the isothermal heat transfer, because heat absorption in the evaporator and similarly heat rejection in the condenser take place at constant temperature. In practically, the constant temperature heat absorption and constant temperature heat rejection is very difficult to achieve. So that's why, because of this limitation, it is very difficult to implement. And the second reason, the expansion in the turbine and compression in the compressor, we assume isentropic, but these isentropic process, isotropic compression and isentropic expansion is practically very difficult to achieve, because there are always heat loss from the system or from environment into the system, and also because of the frictional effect, the rotation of the compressor cannot be free from the friction. Similarly, the expansion of the turbine cannot be free from the friction. So that's the second reason, right? And the third reason is the compression in the wet region. If you see the diagram, similarly expansion of the turbine in the wet region. If you see the diagram like this one, you can see that's a compression process 1 to 2. So that means we are giving input to the compression as wet vapors. So if by using the Carnot cycle, so that means if we give because compressor can work only for the gases, for the vapor only. If we are providing the mixed region, that means the life of the compressor is very low. The compressor can damage very easily. Similarly, in case of the expansion in the turbine, you can see the expansion in the turbine take place in the wet region. So again, the life of the turbine we are compromising. So practically, because of the expansion, compression of the compressor and expansion in the turbine in the mixed region, we cannot implement Carnot cycle for the refrigeration system.